fundamental properties. So we've talked about an object, the property, it's the characteristic, the quality. Then we talked about measurements and quantitative data. And so when we talk about fundamental properties, it's going to seem kind of similar to what we talked about with the 7 base units. And that's that we're going to see measurement units. So fundamental properties are properties that cannot be simplified any further and are described by how they are measured. Okay, so that's why it's going to seem similar to the 7 base units. The 4 fundamental properties are length, which is in units of meters, so very similar to the previous slide. Mass, which is in units of kilograms, same units. Time, which is in units of seconds. And the only addition is that a fundamental property is going to be the charge, units of coulombs. Okay, it's pronounced like coulombs. Coulombs. And then it's capital C. That's the only addition. And these are going to be things we cannot further break down. I can't take the length of an object and break it down any further. Now, data is going to be measurement information that's used to describe objects, conditions, events, and changes. So when we take a measurement, it could be the fundamental data, so its length, its mass, its charge, or its time, we can use that to describe either the object itself, how big something is, how heavy something is, the condition, so the temperature in the room, that's a condition, an example of an environmental condition. Events, so temperature changes, barometric pressure changes, when weather systems come in, and then changes, so chemical reactions, when you take a piece of wood and you burn it on a bonfire, I could take the weight before and the weight after, and I should see that the piece of wood has lost mass to indicate that it's been burned, it's been changed in some way. So some examples of objects, these are just classroom objects here on the left-hand side. These are all things that I could measure, weigh, take the length of, describe the color of. In the middle image and the one on the right, we see weather changes. So green, sunny day, pretty blue sky versus drought, desert, tree with lots of rain falling. And then we have a tornado. So tornadoes are events that we can describe using measurements. Wind speed, length of the tornado path, how long it's on the ground. So those are all examples of measurements and of data that we use to better understand our world. Now, a ratio is a relationship between two numbers obtained when one number is divided by the other number. So, for example, in this box on the left, we have 3 red circles and 1 blue. So this is a ratio of 3 to 1. So we can describe it like you see here. The ratio of red to blue is 3 to 1, or you can describe it as a fraction. The ratio of red to blue is 3 to 1. If I do the same thing with the upper right-hand box, the ratio of green to blue, and I see that I have 1 green, so the numbers are going to line up across the equal sign, and I have 4 blue. Okay, so the numbers I counted up go into the spots right on the other side of the equal sign. In the bottom left-hand side, the ratio of green to red, so I write them out as I read them, green to red, the divided sign goes between them like that, is 2 to 3. And then on the last one, it's a little bit more complicated because now I'm comparing the ratio of 3 objects, and technically we don't have 2 numerators or 2 denominators, we have 1 of each. So in this case, I would write it out as red to blue to green is 1 to 2 to 1. And so the key here is that the order you use must match the order of the numbers. And when you use this fraction, you have to make sure the numerator and the denominator match each other, okay, on both sides of the equal sign. If they don't match on both sides, then what is true is that they are not equal to each other. So we would not be able to put an equal sign. Now, one of the important ratios in science is called density. Density specifically is the ratio of mass and volume. Sometimes it's called the weight density, which is the weight per unit volume. So it's the same thing, but it's weight on top instead of mass. And we will learn later how mass and weight are not equivalent. They are not one to one. You do not have the same mass and the same weight, and we'll talk about that when we get into physics. Now, density is considered what's to be an intrinsic property, which means it's independent of the quantity, meaning it doesn't matter if I have a small piece of cork or a huge piece of cork, it's going to have the same density, meaning all cork will float. Okay, so it's an intrinsic, independent of the quantity. Some examples of things that are not are a bonfire. If I were to go outside on a very cold night and light a single match, we know that that match, the single match, is not going to produce a lot of heat. However, if I took a lot of wood and stacked all the wood up and had a big bonfire, that bonfire with all the wood is going to produce a large amount of heat. So heat is what we call an extrinsic property, meaning that it depends on the mass. How much wood I have. The more wood I have, the more heat that's generated. The other thing that's interesting about density is that it's characteristic of a given material, so we can use it to identify an unknown, which makes it useful. So for example, gold, it's going to have, if I took a 1 centimeter cube of gold, it's going to have a mass of 19.3. If I took this same size block of iron, its mass is much smaller, 7.9. Air, even lighter, 0.0013 grams compared to gold and iron. And then water is unique because water is what we measure everything else in relation to. So water has a density, and you need to know this number, of 1. And we give it grams of cubic centimeters because we take centimeter times centimeter times centimeter. And when you multiply centimeters, 3 of them in a row by each other, you get cubic centimeters. Centimeter to the 3rd power. And we have grams. And the ratio is always going to be mass divided by volume. Okay? So everything is measured in relation to water. If it's less than 1, it's going to float. So something like air will float on water. If the density is greater than 1, gold and iron, that object is going to sink. Now we make predictions about what we know about our objects. Styrofoam will float, cork will float, but we know if we throw a bowling ball into a body of water, it's going to sink. Even though we don't know the quantitative value, the density per se of the bowling ball, we know that based on what we observed in the past, the bowling balls will probably sink. And so density can be a quantitative property, but how we measure it in relation to water, well, we've observed that to be less than or greater than 1 before, but now we're putting a number to it. So this is something that might help you remember the relationship. So density is mass divided by volume, or you can take mass and you can multiply, and mass is equal to density times volume, so that's this one right here. And the other one is that volume is equal to mass divided by density. So you can use this triangle, and the 2 lines up here are division signs, and the line that's vertical up and down is where multiplication occurs. These are all just rearrangements of the formula, and sometimes it gets simplified down to density equals mass times volume. Okay, so these are the variables, the symbols that represent density, mass, and volume. So let's talk about symbols. Symbols represent quantities or measured properties. So in the last one we had density represented by lowercase d. Then we have mass, which was represented by lowercase m. And then we had volume, which is actually a capital V, and that represents volume. Now, symbols are not new to us. Symbols have been part of ancient civilizations and their drawing, hieroglyphics. Those symbols represented words in that case. It was kind of their language. We use the alphabet. Those are symbols, but we put them together to generate words. We have mathematic symbols, so equal signs, divided sign, percent signs, infinity, omega. The pi symbol represents a number. And then we even have symbols that represent cultural things, like this M. You probably thought, well, that's McDonald's. Even though it doesn't say McDonald's anywhere on there, the symbol represents McDonald's. Now in science, we use symbols like density, mass, volume, symbols like this, but they represent a property, something that we're going to measure. Now we take those symbols and we start putting them together, just like we take alphabet letters and generate words. We're going to take these symbols and we're going to generate equations. And equations are going to be mathematical relationships between properties. So how are density and mass and volume related? Well, they're related in a number of ways. We saw in that previous slide that we can rearrange this equation in multiple ways and determine a value about our object. They describe properties, define concepts, and specify relationships. So in this case, we have as the density increases, the mass increases because they are directly proportional to each other. As the density increases, the volume would do the opposite. It would decrease. So it helps us to establish relationships between variables by looking at the equation. So you can see here are a whole host of equations, some of which we are going to see as we move throughout physics and chemistry. So physics and chemistry are based a lot on equations. When you get into earth science, astronomy, and biology, there's not as many equations associated with those subjects. However, all of earth science, all of astronomy, and all of biology are based on physics. We're going to see physics is the foundational science. Everything is built on physics. Chemistry is called the central science. So the principles that guide physics and chemistry are going to guide earth science, astronomy,